Cool. So, yeah, okay. Now it's recording. So from now on, the session will be recorded. I'll stop it when I finish my part. Then the first thing we'll do is we'll look at the problem that we have on recurrent neural networks. I'll pose you a few questions there. So I'm going to share the screen. So this is the problem that I posed to you. Let's see if hopefully you tried to solve it. Unless that was your kind of homework. And then the first question was, if you look at this recurrent layer in particular, how would you formulate it, like using the right notation of subindex and superindex? Basically, that was kind of the challenge. And also like knowing that the activation is a tangent hyperbolic. And that would be the solution for that expression. So what we see is that it's telling you that at time step t, the hidden layer 1, so because we are here, it's hidden layer 1 at time step t, equals the output of the tangent hyperbolic nonlinear activation. Actually, it's this icon you see over here. And at the input, what you do is you have the classic, let's say, weight matrices. Sorry, this one. The classic weight matrices that connects the hidden layer with the input. We call this W1. It's this weight over there. And the input over there. Plus a bias. So this will be a vector bias for layer 1. So that will be a scalar that we would add to each of these neurons. And in addition, the new part compared to what would be a classic multi-layer perceptron is this term over here that's telling us that the hidden state of layer 1 at time step t, actually it's also connected to the same hidden state layer 1, but in the previous time step, so time step t minus 1. And how is it connected? With a new set of weights we call U, and these are going to be weights that will be learned during training through back propagation in time. So that would be the first answer. Any question on this expression?
Just a case of terminology. Well, this is the hidden state, not the output is what I was wondering about.
I mean, I guess that the hidden state is the same as the output of this hidden layer.
But isn't the output what will come out of the RNA?
So the output will be normally when you talk about the output of the whole architecture.
Just the RNA layer. I mean, you use the hidden state to get the output out of a hidden layer, right?
Yeah. Yeah, because the hidden, I mean, it's the same thing. So even in a multi-layer perceptron, this hidden state is not the cell state of the LSTM. Maybe that's the confusion.
Yes, but I'm saying that in case of output, let's say if the output in the number output neurons, that is the layer next to it, are Y, then we have a matrix Y into H or dimension that will compute the output. So I was just wondering if hidden state and output are two different things, because that's what I read somewhere.
In this, okay. So in this example, the hidden state of this layer and the output of this layer are the same thing. In this example,
so this is what will be fed to the next layer. You mean?
Yes, and to the next time step, to both. Okay, I'll try to find the slides from the other day. Yeah, got them. But in this, so maybe what you read, it was referring to the LSTM, because in the LSTM, the state of the cell is different from the output. So in the LSTM, come on, okay, here. In the LSTM.
No. I wasn't talking about LSTM. I was just talking about, remember when we have one to many, many to one, these connections. So if they exist because the output is different from the hidden state. I mean, when you take many input, give only one output. Take only one input, give many outputs. So if the hidden state would be the same as the output, you cannot have so many architectures. Like when you started teaching RNN.
If you do many to one, then normally the output is the hidden state at the last time step. I guess that would be the difference.
Okay.
Because normally that's the case where you, let's say, where you first feed some information to the RNN, and you are interested in the last output of that hidden state, of that recurrent layer. But actually, even if you are only interested in the last output, like in practice, there's a hidden state that it's issued at every time step of the input. Even if you ignore it, it's there. Yeah. Cool. So, oops, not this one, here. So that would be for the first part. And then for the second, yeah. So the second was referring to the counting the amount of parameters, and especially with compared to what hopefully you have seen in multilinear perceptrons. So notice that in this architecture, we have one recurrent layer, and then another hidden layer, and output layer. So the most interesting one is the first one, because it's the recurrent one. That's where things kind of change. If you want to compute the parameters, what you have is this 4x4. What does it refer to? Where does this come from?
Old state to new state.
Yeah, so it refers to this self-connection, the recurrency. Okay. Then this 3 multiplied by 4, what does it refer to from this layer?
From the previous layer to this layer connection.
Yeah, so
XT to W1.
Yeah, W1. Okay, so the 3 and the 4. And this 4, what is this plus 4 at the end?
Bias.
It's a bias. Okay, so you do the numbers, and the other ones, they are just classic multilinear perceptron layers. So you multiply, sorry, the amount of how is it done? The amount of inputs, 4. So in the second layer, you have 1, 2, 3, 4 inputs, and you have 3 neurons, and the 3 for the bias. And then for the last layer, you have 3 inputs for that layer and 2 neurons. So you do the product, and then you add the 2 biases. So you add everything up, and that's 55 in this example. Good. Any question for this? Then last one. It says, now draw the unfolded representation of this architecture for time step t-1, t, and t+1, labeling the edges with the appropriate weight matrices. So just in case you don't remember, maybe I should have added it. Maybe I can add it there. Small one, small version of the forward version. Much better now. Oops, come on. So now remember that rotation that I mentioned the other day. This is the input data. So this dimension 3, but we don't see the 3 dimensions. They are across the screen now. So it was asking for t-1, t, and t+1. So this is why we have these 3 inputs. And here we have the weights that go into the feed-forward direction. This W1, W2, W3, the ones that you have noted here. Of course, they are always the same at every time step. Now, as there is recurrency only in the first layer, this is the layer we connect with the weights U that across each time step, they are always the same. That's what I indicated here with this U. This is what's called the unfolded representation of an RNN. Any question on this? No? Good. So these slides, you have them on already in the digital campus, so feel free to get them to study for the exam. Okay? And we can move into new material, which is this video architectures. Excellent. So before I begin, I will also encourage you again to turn your cameras on. That makes the whole experience much better for me and also for your colleagues. So if possible, turn your cameras on. You are very encouraged to do that. Then the topic here is called new architectures for video encoding. So for now, the other day I really gave the basics of RNNs, and there was not much video involved, and today it's going to be the opposite. I will just assume that you know a lot about new architectures, and then just focus on how we can apply the most of the architectures you already know to analyze video. So acknowledgements to previous students who have helped me in preparing this lecture or working together in this type of architectures. So this is the task that we are going to be using today, kind of guiding the discussion, which is called action recognition or activity recognition. It is kind of an ImageNet-like task in which, given a video clip, that these are the examples you see, we would like to predict what activity in this data set. It's a data set of sports, so the activity was what sport it's being depicted. And there are like with some level of confidences. And basically what you see here are the top 3 predictions of an algorithm for these examples. So now, obviously, this is a series of images, of video frames. So we are going to analyze videos. And this is going to be the leading application. Of course, we can think about a million applications for video, but to drive the discussion, I will always be assuming that we will be solving this task. And later, in the future, in the program, we're going to address other tasks, the task of object tracking and video of the object segmentation. So that will be the kind of application of task that we want to solve, which action recognition. So let's see how to address that. When we think about videos, actually in a formal way, we can consider videos as 3D signals, in the sense that in order to know the signal, the value of that signal, we would require the X and Y coordinates, which would be like that would make it a 2-dimensional signal. But in addition, now we also need the temporal coordinates. So we can think about videos as volumes, 3D volumes, which in addition to the classic X and Y coordinate, now we also have the temporal dimension. So whenever we fix T, what we obtain is a video frame, an image. So we can think that videos are sequences of images or time series of images, if you want. So what we know so far, you have already looked a lot at how good convolutional neural networks are in order to analyze images. And that's mostly because of the translation invariance property that convolutions have. So when you have a cat in an image or in a video, never mind if the cat is in the top left or top right position of the video, of the image, it's still a cat, okay? And so we are, by exploiting that convolutions, actually they behave, they are invariant to translations. We can reuse the convolutions at any location, and that allows us to save many parameters and allows us to generalize much better to all this framing of the cameras that you have over the objects. If someday you have some application in which really the position of the object in the image is important, then maybe you should add something else in addition to convolution to really encode the absolute position of whatever object that you may have in the image. But in general, they are, if we don't do anything else, convolutional neural networks, they are good tools to encode and analyze images. Okay, so what can we do if we want now to, based on what we know for convolutional networks, what could we do to process now sequences of images? So this is kind of an open question for you. If we want to solve this task of action recognition, so given a sequence of video frames, maybe, and we would like to learn a function that, given this sequence of video frames, it will predict a label, like the activity. What options can you foresee? Open turn for you. What could we do? Maybe we can think about the most basic one before you start jumping into very complicated solutions. What would be if somebody tells you, okay, I would like you to design a solution that, given a sequence of video frames, in the end, it will tell me which activity is in there. What would be like the very obvious and...
Taking a CNN, taking out the features and putting it in a RNN or LSTM.
Okay,
Maybe.
yeah. Okay, so that would be totally an option. Probably it's not the easiest one, but it's an option, totally.
Simplest thing maybe would be to just give all the last 5 frames to the network, maybe.
To what network? So I guess the question, like, which architectures you can think about? So what you're trying to do is saying, like, let's just use the last 5 frames. I guess you're trying to decrease the computation requirements, which is good, and that's something that probably we want to do, but more in architecture manner. So imagine you have this, right? You know what this is, an inception, or you have a ResNet, or you have whatever network you have that works well with 2D images. And now what you want to do is, given a sequence of images, video frames, you want to solve the action recognition task. What would be the most easy thing to do?
Use the CNN for each frame.
Yes, excellent. And
with a 3D convolution.
Okay, that's not so easy. Let's leave the 3D for later. Okay, let's keep now in the easy CNN, 2D CNN. So okay, so if we have a CNN that we apply to each frame, then the CNN, and so of course we assume that we have a data set, a labeled data set, like this one, right? We have a data set where we have, for each video clip, we have a label, and so we can train our CNN, 2D CNN with labels. But that's, so we take our training data set, we extract frames, we label each frame with the activity, and then we train our ResNet or whatever architecture you want. And now at test time, what we have is like a sequence of 6 frames, and we feed this one for network, this one for network to network, and we end up with 6 predictions, right? One for each frame. So
Yeah.
what else can we do now?
Then take the majority of the prediction and use that as the overall prediction.
Okay, cool. So that would be the simplest option. Okay, and maybe it's enough for many applications. Then, okay, somebody else talk about CD3NNs. Do you want to talk about it now?
Well, I think basically the concept is pretty much the same as Pablo was saying, but instead of using 6 different CNNs, you can just use a 3D convolution, and you keep the spatial features in the first 2 dimensions, and the 3rd dimension is basically different frames.
Okay, yeah, good. Look, we will look at them later. I'm not sure. Have you seen 3D convolutions previously in the program?
I don't think so.
Okay, cool. So probably you have, but I will assume that nobody has. Great. So this is the outline for today, which basically there's one option that I didn't give you time to talk about, but probably you don't even know yet, which is option number 4. But these are the first 3 ones you already mentioned them, okay? Whether we process each frame separately or we introduce some kind of spatio-temporal convolutions, 3D convolutions, or we connect CNNs with RNNs somehow. And then there's this fourth option that I'll comment, and then in the end, some more exotic solutions. Okay, so this is the outline for today. Let's look at the first option that historically was the first thing that people tried to do. Is that okay? So why not we feed each frame separately through the same CNN in general, and then somehow let's combine. Let's see how we can combine the features or the predictions. I mean, we could whether for each frame really predict a label and then pull whatever, or what we could do is to at some point, maybe not the last layer, but at some of the previous layers, we keep those features that the CNN provides, and then we average them or we pull them somehow, and then finally we predict the label. So that would be one option. If we apply solutions like temporal pooling, something like the max of the predictions, I think that you mentioned the max or the I don't know, you said something else, the median or whatever. So one way in which you pick one value or the average. There's a problem if you do that, which is that when you do pooling, you lose the notion of order. So then if the order in which the frames were appearing was relevant, maybe you want to capture some type of motion between frames, this is lost once you do the pooling. But it's a first approach, so that's fine. So this will be the single frame model. And actually, at the very beginning of dealing with convolutional neural networks, there was this work. So it's 2014, so it's been a long time. So it was just the beginning of the deep learning craziness. So there were some other options that using 2D convolutions, actually what they did is they instead of just looking at each frame and treat them separately, they combine, let's say, given a video clip, combine the first and the last frame. In this case, they would go through different towers of the same network and then maybe some fully connected layers on top. This will be convolutions and this will be fully connected layers. Or maybe what you could do is stack some frames to try to capture something more on the temporal domain, let's say. So you stack everything, but then still in this work, everything were 2D convolutions. So even if they stack it, it's not, the convolutions were always 2D. So the depth of the first filter, it was matching the depth of the input.
One question, what do you mean by stacking the images?
So for example, when you have a color image, probably what you have seen is what you do is that you stack the RGB channel and then you feed into the network.
Okay.
Now imagine that you have 5, there are 5, right? 5 frames here. Then you take the 5 RGB channels and just put them all together. So that's 15 channels. So we'll be like training a 2D convolutional network in which the input has 15 channels.
Okay.
And what I was mentioning is that in this work in particular, what they did is that the depth of the filters of the first layer, they were also of 15 depth, 15 channels. Okay, so they were not 3D convolutions. When we do 3D convolutions, we move in 3 dimensions, the filters, and in this work they were everything 2D. Or we can do like something more exotic. Anyway, they made this work and they compared different solutions, and they observed that the slow fusion was the best option. But no, man, I think it's not that important. Just that you know that there was this one. This was one of the first works that tried to do something special for video when trying to solve action recognition task. What is nice now is these first models, they actually they were considering these stacks of RGB frames. We can visualize the filters I don't know, did you have any lecture on visualization of convolution of filters? Yeah, okay. So these are temporal. So these are 2D convolutional filters, but they are, let's say they are RGB. So RGB at time step 1, RGB at time step 2, RGB at time step 3. So they are aligned with them. So we can visualize, if we just plot the RGB's filters, the filters that correspond to RGB channels, one after the other in time, we can have these nice animations that you see here. So what we observe is that the filters that they learn, they are not random, and some of them, they capture some kind of temporally frequency patterns. In addition to the spatial patterns, also some, okay, they are hard to interpret, but also some temporal patterns as well. Second option, spatiotemporal convolutions, which means just a reminder to make sure that we are all in the same page. Remember that when we do spatial to the convolutions, we have whatever input feature maps, and that then we choose how many convolutional filters we want, and that's what defines how many output feature maps we will have. And also remember that even if so far in still images you have seen spatial to the convolutions, that does not mean that the filters are 2D. What it means is that the filters, they move. They move. Actually, they don't move, but you can think that they are moving over 2 dimensions over the input tensor. Okay, so if we do 2D convolutions over this tensor of depth 4, it means that we move in this horizontal and vertical direction. But actually, the filter, it's whatever width, whatever height, and the same depth as the input channels. Okay, that's what you have seen so far always in convolutions 2Ds. And that will be if you have one filter. If you have many filters, then all filters in this case, they are 3D. So in case you didn't notice, filters that apply to the convolutions, actually they are 3D filters because they also have this depth channel. Now, this was a reminder. Now, this was a reminder to explain that there was this idea of spatiotemporal convolutions. Actually, it has been out there for quite a long time. For example, in 2010, also there was already this work from Jan LeCun and more. I guess they are people from NYU that already introduced these 3D convolutions. At that time, nobody paid attention to deep learning. 2010 was before the AlexNet craziness, but that was already there. And then actually it became much more popular 5 years later with this work called C3D, in which basically what they did is they allowed the convolutional filter to also move in a temporal direction. So let's assume that we have a volume which will be a video, okay? And now what we're going to have is a convolutional filter that moves into this volume. So this large volume of the video, this is the W and H volume, and this depth may represent the time dimension. So that would be, if the large volume is this one, the dimension will be 4. And now when we have a 3D convolutions, what is very important is that not only we're going to move through the height and width directions, but also across time. So this weird arrow here is telling you that this convolutional filter, it's going to be not only positioned at different spatial locations, but also at different temporal positions. Okay. In order to do that, it's necessary that the depth of this 3D convolutional filter is smaller than the depth of the video clip that we are processing. Because if it's the same depth, then we don't have any 3D convolution anymore, because then we cannot shift the filter in the temporal dimension. It's already on the limits. Okay. Then when we do 3D convolutions, again, so this you can think this is a grayscale video, which makes things much easier. But If it was color video, then there would still be a fourth dimension for the filter. So the filter would have like the two spatial dimensions, the temporal dimension, and the fourth dimension, one for each color channel, which I don't know how to draw, but that's the shape of the filters. If the input tensor is had more than 3 dimensions. Okay. Cool. Of course, we can have 3 convolutions. I guess they are quite easy to understand if I think about the first comb layer, because that's what you apply over the video. In this case, a grayscale video to make things easier, but they can be in any layer of the network. That's nothing. As long as you have like tensors that keep alive the temporal dimension and that you can move your convolutions that direction, you can have 3 convolutions in any layer of your network. Okay, then just how did they, in this work, how did they deal with this problem of action recognition? So actually, in this work, they made something kind of simple, which is like they, given a large video, they created clips of 16 frames, and actually they somehow process each of these 16 frames clips separately. So they train, let's say they train a neural network on clips over 16 frames. At that inference time, what they did is when you had the whole video, they would take the video at test time, cut it into segments of 16 clips, and then do some kind of temporal pooling, whether of the features or the activities. Okay, maybe you can think about it over the activities, just to make it easy. So at the end, they would predict the activity for the whole video clip. Then, question for you. Working with 16 frames clips of a longer video, instead of the whole video, there must have been a reason to do that. Because why would you want to break your video in clips, right? If you have the whole video. These are 16 clips from the same video. Why did you think that in this work they really splitted the videos in small clips?
GPUs.
Can you repeat, please?
GPUs, I mean, they didn't have enough memory to fit the whole video.
Yeah.
That's why.
That's the issue. So when you start dealing with video, you super quickly run out of memory, and let alone if you try to do things with 3D convolutions. Because 3D convolutions, the filters, like, they will grow the memory requirements compared to a 2D model. They will just grow for each new temporal dimension. So every time you increase D in one unit, you are multiplying. So you're kind of multiplying the requirements of memory that you need. So they are very demanding in terms of memory. So I think that one of you was trying to do things with 3D convolutions. I'm sure that, did you try this? Did you observe anything?
Yeah, well, it's pretty much slower than using 2D, that's for sure.
And do you really cut videos? Do you work with short videos?
Yes, actually, it's like 300 frames each video, and then it's clipped to 32, I think.
Okay, yeah. So that's quite classic to do when dealing with 3D convolutions, because you will very rapidly run out of memory. Okay, then in the world of video at that time, actually, but it's a bit, the figure is from a little bit later, but of course in still image there was this ImageNet data set that you have known about, maybe some other ones, and basically what they said is that okay, so there was all these models on ImageNet that were kind of improving the results by adding more layers. And this allowed not only to solve ImageNet, but allowed to evolve, to advance very quickly in other tasks like object detection or image segmentation or image captioning when you do it. I'm not sure. I don't know if you have already done these lectures, but if not, you will. So the features that we'll learn with ImageNet for image classification, later you can transfer them to other computer vision tasks. Then for video, the strategy is kind of similar, but now instead of using ImageNet to train models that we can later transfer to other tasks, there are some data sets out there that try to do the same that ImageNet did for still images. So, for example, there are some others, but one of the most popular ones is Kinetics dataset, which it's much larger. So there are 300,000 videos, which in terms of number, it's smaller than 1 to 2 million images. But notice that in each video there are thousands of video frames. So actually, this dataset is really large. This is for action recognition, at least. Maybe there are more labels. But the idea is that if we want to have models that are able to train networks with much more parameters, like networks that deal with 3D convolutional neural networks, we need also data sets suitable for that. So kind of ImageNet for videos. And Kinetics it's one of them. There are some others. But the idea is that if we pre-train models that are suitable for video, for action recognition video, later it will be easy or possible to transfer them to other tasks related to video, like object detection, but in the sense of on video sequences or video summarization, or computing something called optical flow that we will comment later. What is that? And that's the idea. So the same approach that you probably have seen in still images of having some models that are pre-trained and then I transfer to other tasks, that also applies for videos. There are some models out there that are pre-trained and you can use and transfer for your own task. But as there was already this effort, or there has been a huge effort in training models that are good for ImageNet, for image classification, why not trying to exploit what we already know, or the models that we already have trained for still image classification, to initialize models that will be based on 3D convolutions? Okay, because in the end, they are all natural images, and video sequence in the end, they are sequences of images. So do you think that we could use the weights that we learn with a ResNet or whatever, and to initialize the training of C3D? So the idea is that first I have my whatever model, I train it on ImageNet, 2D convolutions, and now I want to initialize a 3D convolutional model with the weights that I learned from 2D convolutions on ImageNet. Do you think we could do that? How could we do that?
You could take the weights from a 2D convolution and just copy it on the depth of the 3D convolution.
Yeah, great. So that's a very good answer. If you have done it, you had that answer in 2016, now you'll be very famous and working in DeepMind because that's what they did. They developed this idea of inflated weights. And when you see this I3D, that's what it means. It means that in order to initialize, again, to initialize the training, what you can do is, like, if you have my 2D convolutional filters, in order to inflate them, what I'm going to do is I'm just going to replicate these weights in depth. Okay, and this is also a very popular model. It's one of these models that you will find online very quickly. It's called I3D. And what it's very interesting is that it was first initialized with ImageNet weights and then trained with Kinetics or whatever other data sets. Yeah, the Kinetics it was trained. But they did this and something else, okay? But that's one of the main contributions they did. Later I'll explain what else they did. But that was one. Yeah, sorry.
So if we're copying weights, let's say from 2D to 3D, a lot of filters have the same weight now, and they will be connected to some layer after that, right? We're assuming that, okay, we've copied some layers and now there will be some layer after it. So when we do backprop, what will prevent the layers from learning the same features? Since they're a copy of each other, we're not sort of breaking the symmetry between the layers. So what will prevent them? Because they will get the same, from the upward gradient that they will get will be the same.
No, but
then,
you are.
But the input is different.
Yeah, right.
I mean, the original ImageNet, the ImageNet trained network, the weights there, they are different on all layers and in all filters, so they will be different.
Yeah.
No, sorry, you're talking about this one. Yeah, but the input is.
But yeah, Edward answered it right, that since the input will be different to each of them, the gradient will be different.
Yeah. That's it. Thank you. Good. Another idea. I hope you've learned about residual layers. Yes, great. So remember, the residual layers mean that there are skip connections that allow to more easily learn the identity and skip layers. Okay, so this is, if you know about residual layers, you must know about ResNet. And maybe if you read the paper or somebody talk about the paper, you'll know that in the paper they present some small versions of ResNet with 18 layers and 34 layers. And then these layers, they are grouped in blocks, they call them. And in each block, there are a couple of layers. So let's focus on this one. A couple of layers with the size, the spatial size of the filters, and this the amount of filters. So these two layers will be like these two. Okay. Great. Then imagine that you inspired with this 2D ResNet that it was done whatever. Now we would like to have a 3D ResNet. Okay, so let's just say, so the story is like whatever we learn in ImageNet, let's try to transfer it to video. So what would change if we wanted to define a 3D ResNet from this table? What should we change? By one. Now I'm not talking about any pre-training. I'm just saying like let's change the scheme. Like just change this table. What would change if I go from a 2D ResNet to a 3D ResNet?
The 3x3 kernel. That
yeah. These 3x3 kernels, now they will not be 3x3. They will be 3x3 but something else. And just to make it easy, we just also do 3x3x3. Okay. So I'll call this 3D ResNet in the next slides. 2D ResNet and 3D ResNet. So if we try to solve this task of action recognition with a 2D ResNet with the same amount of parameters, with a 2D ResNet with the same layers and a 3D ResNet with the same amount of layers, that's the performance you obtain. So you can observe some gains, okay? Res3D, it also works better than the classic C3D, which also makes sense for everything you know about residual connections. But then I have a question here, like, okay, so this Res3D works better than the 2D ResNet, okay? But do you think, if I look to these values of accuracy values, do you think that this comparison is, let's say it's fair? Or, I mean, can I just say that, yeah, Res3D is better than 2D ResNet? Or
you also have to take into account computation time, I guess.
Yeah, excellent. Yeah. So the message here is that, okay, if we really look at accuracy, I guess, yes, they are better, but we are introducing so many more parameters. And that's something we need to be aware of. Okay, and because there are trade-offs, and if you're going to deploy a system, that's something you must be aware, like how much computation you need. So here you have a comparison between these two models in terms of parameters and floating point operation per second, which is kind of means like how many multiplications more or less that we are going to be doing. And if notice that these gains of performance that the 3D ResNet has compared to the 2D ResNet. In terms of parameters, so it means like memory footprint, they are always almost 3 times, which is expected, right? Because we are adding like this per 3 channels in time. And in terms of computation, it's much more than 3, because actually there are convolutions that we are planning at multiple locations. So this gain of accuracy comes, of 3D convolutions, it comes to a very significant cost in terms of computation, especially memory as well, but in computation a lot. I think that already like that those of you, I don't remember what was the name of who was working with 3D. Can you tell the name?
Me, Eduardo.
Eduardo, okay. So they already mentioned, yeah, that takes so much computation. So this is what Eduardo just explained, but with an experiment. Okay, so keep that in mind, that maybe accuracy is not always, it's not the only thing you should look at when deploying a system. Maybe you are not interested with these 3 points of accuracy. Maybe you really don't care, as long as your system can run much lighter. You can run it in a embedded device or mobile device. Okay, there are other intermediate options which are called mixed convolutions, which these are layers that some of them they are 3D and some others are 2D. Okay, so in these mixed convolutions, the first layers are 3D convolutions, the last ones they are 2D, and there's this this word that kind of says that if given a fixed amount of parameters, okay, and then given a fixed amount of parameters, and you use these parameters whether with 2D residual 2D connections or with these mixed convolutions, so the accuracy can be better. So you can kind of obtain with comparable capacity, so comparable amount of parameters, combining some layers with 3D and 2D works better, and performance can be better or more or less the same as 3D convolutions, even if they require three more times parameters, 3 times more parameters. Okay, so these mixed convolutions, they are kind of a sweet spot between 2D and 3D. So just not have the whole network with 3D convolutions, just have a few, the ones on the first layers, basically. Also, they try what if you had the 3D convolutions on the deeper layers and first the 2D. It didn't work as well. So just you can forget, but in case you were wondering, it doesn't work so well if you just do the reverse. And also they require more parameters. So it's a bad idea. So if you want to do some of these intermediate things, first apply the 3D convolutions and then deeper layers 2D convolutions. This is another variation, which are called pseudo 3D residual, which basically they go into a direction of splitting. Okay, I think I skipped this, but making a difference between the spatial convolutions and temporal. So this would be the classic convolution, so residual unit. And this is what they called pseudo 3D and residual. So residual is because there's always a residual layer, that's the easy part. And the pseudo, it's because notice that in addition to these bottlenecks that you have here, that they are just there to reduce the amount of channels. First, they apply spatial convolutions and then temporal convolutions. Okay, the spatial convolutions and the temporal convolutions, but separately, whether one after the other or whether in parallel, and then later they do the addition, or maybe first with the spatial and then some residual parts. So all these very weird ways of combining spatial and temporal convolutions. And then they invented these blocks like with a sequence of these types. So these different versions, P3D-A, P3D-B or C, different sequences, whatever. So they propose this and it works slightly better. But actually this is the step before, I guess, to one of the models that is more successful nowadays, which are called the convolutions 2+1D, okay? Which means that now, instead of doing like these 3 convolutions, really split them in first spatial and then temporal convolutions with, actually you could have multiple temporal convolution filters over here. Okay, I don't have time to look at this, but maybe you can think about this for, well, just look at this, okay? Just in case it appears in the exam. So you have the answers, but just counting the parameters. But basically the idea is that given the same 32 by 32 filter, the amount of parameters that we have with 3D convolutions is much larger than when we have with C2 plus 1 convolutions. Okay, I think I'll explain it in detail. Don't worry, never mind. So imagine the question says compare, okay, I'll do it. Compare the amount of parameters required in a layer of 32 convolutional filters with spatial size D3 and temporal size T equals 3. So it's the same in the temporal and spatial dimensions for the C3D or C2D 1D cases. And let's ignore the bias. And consider Mi equal 1 means that consider that there's only one of these temporal filters. So if we think about the C3D convolutions, if we consider one single filter, the amount of parameters is 3 by 3 by 3. So just everything is 3, 27 parameters. If we consider that the layer has 32 filters, that would be the amount of parameters we have. Then on the other hand, if we just kind of disentangle the spatial part over here, then first we have a 3 by 3 filter, it's this part, and then one temporal filter you add. So the trick here is that at this point we are adding, and in this point we were multiplying. So in one 3 by 3 and then another 3 filter, the total amount of parameters is 12. If we had 32 of them, it would be 384 parameters in total, which is much less. So this makes, so this way you have a network that still has the capacity to learn patterns in the temporal domain, but you don't need to have as many parameters. You can reduce the amount of parameters. And this is a comparison of everything we have seen compared to this, okay, to the residual version of the 2 plus 1 convolutions. In this axis, you have the accuracy, but also notice that in this other axis, I'm adding the flops, so the computation, the floating point operations. And you can see that you can get much better accuracy with more and with a high amount of floating operation per second. So that's quite efficient in that sense. Okay, but we are just, so everything you have seen in still images, we are applying it to 3D. Have you seen about separable convolutions anywhere? Yes, great. So same story that was introduced in the exception model. So also there's a work called CSN that it's combining residual 3D and separable group convolutions. Same story, and it works. These are these ones. So this is accuracy. So this works even better than the residual 2 plus 1, and with less gigaflops than R2 plus 1D.
Just a quick question. What is the MNIST for videos dataset?
The MNIST for videos. Okay. So the MNIST, it's called UCF1 and HDMB and HDMDB because they are small, smallish. I guess the MNIST is okay. First, there's a dataset that's called moving MNIST. So depending what you want to do, these are MNIST digits that move around.
No. I was asking something like normal videos, but something you can do prototyping on.
Yeah, I think it's HDMB, and I don't know if they are in any of the tables. but AGMB, I think it's called, and UCF 101. But these people, I mean, so these DMs because they are small, but all these papers that I'm talking about, I think they provide normally results with kinetics at least, and some other data sets, but at least with kinetics data set. Okay. It's about time to finish, so I'll finish here, and I think it's not necessary. We can finish this when we have more lectures in the future. I think it's not a big deal. So yeah, let's just you should take some break now before the next one, okay? And we'll finish this next time you have lecture with me, which will not be next week, okay? But just check it out. Great, I'll try to remind you next time we meet. Okay, so take a break, please. Bye.
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 Oh, una pregunta. Bueno, Xavier.
Yes.
Si es pot, perquè si estem en break,